the book goes to equality before it covers the exists quantifier. And I wrote some examples of how to do what you would traditionally think of as equality, since it's a little bit confusing sometimes how they introduce it in the book. Specifically, the difference between equality of expressions and equality in terms of equations. So the book covers substitution, or this is like rewrite. This is rewriting using an equation as a hypothesis inside an expression, right? So this eq.subs h1 is going to rewrite this equation inside whatever this expression is. And like in this example, this expression doesn't need to be an equality itself. It just needs to be an expression. It can be arbitrary. But that's not the only form of equality. So there's also equations, the form of equality where you have an equation and you want to rewrite it in terms of, you want to do something either to both sides of the equation, or you want to show another equation derives from that. And it's a little bit unclear how to do that, right? They give, they talk about calculational proofs, but they don't actually say that you can't do the second thing with calculational proofs. So these are actually only for expressions. And what that means is that they start with an expression, and then there's a sequence of operations, I guess you could do on them, which would be these tactics or functions to transform this expression into eventually the end expression. And the calc block as a whole is going to have a type of this expression and this last operator and this last expression, right? So if you finish with, you know, A equals B or whatever equals C, and then finally you get to less than D, the calc expression will be A less than D, as an example. Oh, here they do one with E, right? So A equals E, A, blah, 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 E. But this doesn't tell you how to work with equations themselves, right? How do we show kind of equality on equations? So to do that, there's a couple ways of doing it. It's difficult to do it with calc. I'm not sure it's actually impossible to do it with calc. I mean, like you could have, you know, try to use like if and only if instead, and then have it equals on one side and an equals on the other side. But that would be a little tricky. And that's very rare to see, if at all. So instead you use specific tactics and specific functions, namely conger and conger arg. But I don't think, does the book get to this? Let's do a little search for this real quick. Yeah, so conger arg, it's interesting how it's related to substitution, because they're very closely related. Obviously, they're both to do with equality. It's just that conger arg is meant for functions, and to transform a function, to transform an inequality, you can do that by applying a function to both sides of the equation. Usually, you know, if you're doing algebra, this would be like adding something to both sides or subtracting something from both sides. That's really just applying a function to both sides. And conger arg is the lemma, I guess you could say, that you can use to show that that is still equivalent. And of course, to go backwards, you can use conger arg as well to show that, for example, fa equals fb implies a equals b, but only if the functions are what's called injective. And that's for later on. Okay, but enough of that. I wanted to show a quick example. Well, maybe it's not so quick, but I wanted to show an example of equality and how to do algebra, because even though this isn't what the book's doing, I mean, it's just, it seems unreasonable to me to expect people to do so much lean before getting to algebra, right? Like, you should know how to do algebra, or at least have some notion of how to do it. So in the first two examples here for episode 11, you can check out the file. Link is in the description. I used calc with an example of how you would, you know, in real world code, you would probably be doing some kind of library search or something to show a step-by-step proof, right? I would, you know, usually you get stuck here somewhere and you know, let's say you're having trouble showing that b is less than b plus 1. You can use exact to narrow that goal. And what I'm trying to illustrate here is not just that you can use, you know, obviously you already know about library search, but that if you have a proof of the form A is less than D, you can use calc to narrow, sort of to make it more explicit, right? If you can't prove right away with library search that A is less than D, like, let's see if we can. I'm curious now. Perhaps we can show A less than D by exact. Right, so it looks like we cannot do that, but we could show something in between, right? We could show a equals b. This does have something, right? So if you know already, like, or if you're trying to figure it out, your proof, it really helps to do step-by-step goals. And if you get really stuck on something, you can make it very, trivial, like the steps between each one. You can keep adding steps that are super trivial. And that can help sometimes figure out, either to do library search automatically or manually or some other tactics, right? And we'll get to the other tactics, like the more powerful tactics. So yeah, in this example, I'll just cover it briefly. I added a lot of comments, so you should be able to read those and see what I'm trying to show here. Basically, this problem is I forget what you call it, a system of equations problem. And so you have multiple different equalities that you need to manipulate and then use, right, with each other, with respect to each other. And so, of course, with substitution and rewrite, you can, of course, do that by, you can rewrite. And I think here, h3, for example, is already in the form of some variable equals some expression. So if I go down here and I find, yeah, you can do substitute h3, and actually h2 is as well, because even though the a is on the right side, it doesn't matter. It can still be used by substitute. But how do we work with h1 to get it into the form that this is solvable after we substitute a and c? And so that's, of course, algebra. And you do algebra of this nature, such as moving, isolating a on one side. You do this by applying a function to both sides. So that looks like this, congr arg, and then I do section syntax to create an anonymous function to give here. And this just means create a function and put its argument on the right side. Sorry, that's the left side of the subtraction, which is our operator that takes 2 arguments, but we are making it into a function that takes 1 argument and is specialized to its right-hand side being 3b plus c. And we're going to do this on both sides of this equation, h1. And so you'll see after that I have a new lemma with that on both sides. And so in this case, and this is just the way I like to do it in Lean. There are plenty of other ways, but I like to do a have statement, and sometimes I'll give it a name like new h1 or something, but usually for stuff like this, it's not very necessary. And that way you don't mess with the original equation because sometimes you don't want to do that. And so, okay, after that, we just do a rewrite of this to cancel. If you ever have trouble canceling the operations on both sides, right? Like here, obviously it seems like this expression should cancel to 0, to just a. It's usually because the first reason is perhaps like you're trying to cancel multiplication and division. Actually, let's just use this example. So suppose you're trying to cancel subtraction. So if you were trying to cancel subtraction here, this would work for natural numbers. But if you were trying to cancel subtraction of the form a minus b plus b, that would not work for natural numbers unless you had a proof that a was bigger than b, because you're not allowed to do subtraction in natural numbers without you're not allowed to mess or not only just do subtraction, but cancel it or do anything with it with natural numbers unless you have a proof that the subtraction is possible. And same with division by 0 and the other functions that are, have restricted domains kind of. So yeah, and the other way that you can get into trouble with this is it can be a little tricky. So in this example down here, now also disclaimer, this proof is definitely not the best way to prove this. This is just some random proof that I came up with, and I wanted to illustrate, like getting into problems, getting into difficult places with Lean. And this is definitely a difficult place because what happens is we get to this expression here and we see that we have 3, no, sorry, this is too far. We see we have 3 plus b times -3 plus b times -1 plus -1 on the right-hand side. And of course, we want to simplify this to b times -4. So you might use this function that it's not quite so straightforward, right? We have to apply associativity of add to get the -3 and the -1 isolated in parentheses so we can actually add them. And that would be with add associative, this function for ints. But the problem is if you try to do this naively without the 3 here, what happens is Lean applies this on the left-hand side. And if you try to say, well, okay, I know how to apply things to the other side, I use a convert tactic, convert at h1, and we're going to go to the left-hand side instead of rewriting at. Well, then what happens is it's kind of weird. It seems like nothing happened. I still have the b times -3 and the b times -1 plus -1. Doesn't seem like much changed. And if you play around with this a little bit, you'll find that it's quite impossible to do this with convert. And the reason is very subtle. It's because of the implicit parentheses around this plus. If you hover over it, and this is where hovering over things can really help you, you'll notice that this plus is grouping the b times -3 and the 3 together in parentheses. And that means that when you try to apply a lemma that takes something of the form a plus b plus c, it's going to see this as a plus b in parentheses plus c, and it won't match. And you might say, oh, okay, that's trivial. That's like, why can't Lean know? Remember that the way it has to be consistent, right? The lemmas have to do what they set out to do and no more. If you have too smart of a tactic or a lemma, the more it can get into trouble. Things like mul, assoc, mul, add, assoc, what these lemmas that do things that, so for example, the commutativity of add, right? You can apply that to many places here, and you can keep applying it indefinitely. So the more powerful they were to make these tactics and dilemmas that the tactics use, like rewrite, the more likely it is and the harder it is to avoid getting stuck in loops, right? Or doing nothing productive. So that's why, that's my understanding of why it can be really tricky to apply a lemma like this. And a big part of this is that a really good way to avoid this problem is to first put everything into normal form. And an even better way to avoid this is, unfortunately, Simp didn't quite do this, but if you had something like norm num or ring or whatever, all of this algebra is trivially done with those tactics and with MATLAB, which we'll get to anyways. So this really isn't such a big problem, but it is worth understanding, especially because it can always come into play later on, even if you're not doing algebra. All right, so let's put it back to where it was. And I think that's about it. I'm going to talk about all I'm going to say about this proof. The rest you should check out yourself. There's nothing much other than those two main things, but you're welcome to step through and see, and of course also try to finish it. I would recommend, if you try to do this proof, that you do it your own way. Now we actually go on to exists.